All right. There's my beautiful mug. And we want to do, it's already started recording. Enter full screen. There we go. Now, let's get the board up here. All right. The whole idea behind this, if you've not, none of your instructors have used Zoom before. Have any used Zoom? Okay, this is not, okay. What I'm trying to do is record the session so that I can put it on Blackboard and you can access it. And if you can't make it to, for some reason, you're somewhere next to a computer, you can log into the Zoom. Just go through Blackboard, log into the Zoom, and you'll be part of the interaction. We can hear you. We have a little thing up there with your picture in it, as long as you've got a webcam on your laptop or your desktop. And you can ask questions and interact. And all of that's recorded. Okay. So let's see. 3.5. I'm missing some. See, there you go. So I'll put this on Blackboard, assuming I can figure it out. And then those who are missing, or if you just want to look at it later, say between now and Wednesday, review the review. Let's see, we've got chapter 3 and 4 to review, right? Okay. Let's go over here and let me get out my document. Here. And just work on those two. Probably need my calculator too. Okay. So let's see. What are we covering here? They're separated into two groups, I believe. Yes. Up through page 17 is chapter 3, and then from 18 on is chapter 4. So let's see if anybody has any trouble with chapter 3 first. I would be surprised, unless you're an algebra whiz, that number 1 gave you trouble. Okay. And I assume that it's probably the algebra. If you go back to the original definition for weighted average, then 1 becomes a bit easier to swallow. So let's do number 1. First of all, if you want the average molar mass of an element, you need the fraction of the let's see, how do I write that? The fraction of element 1 times the molar mass of element 1. Right? Then you have the fraction of element 2 times the molar mass of element 2. Let's just, for argument's sake, just say we only have 2 isotopes. Molar mass, I should say isotope 1 and isotope 2. Right? Because that's what we're doing. We're taking the isotopes and their relative abundance. Oh, I forgot to divide. No, I don't need to divide. Sorry. Why? Because the divisor is already incorporated in the fraction. So you remember, before we get to the problem, you remember what we did with carbon, right? If we say the molar mass of one isotope of carbon is 12 and the other is 13, and this one is, say, I don't know, I'm just making this up, 0.99 is carbon 12, and the rest of it is carbon 13, right? Then you do those together, and you end up with 12.01. Okay, everybody remember that? Okay, so now that we know that, let's take the actual problem. Copper 63 and copper 65. So we have that isotope of copper and this isotope of copper. And the question is, what's the approximate natural abundance of this one? Right, so we want the percentage of that one or the fraction of that one. If we only have two isotopes and we let the fraction of this one be X, then this one has to be 1 minus X, right? Because they got to add up to 1. Right? Add up all the fractions, and the total equals 1. Now we're given one other piece of information. The average molar mass is 63.55. There you go. Atomic mass units. So that's the average mass that comes from this calculation, right? So if this is the fraction of copper 63, then that fraction times 63 is what it contributes to the total. And then this fraction times 65, that's what it contributes to the total. And both of those together, added up, is 63.55. We're good so far? Okay. Now, one thing you can tell just by looking at this number, which one of those isotopes is the lion's share, is the majority? Which one's closer to 63? This one. So X is going to be a lot bigger than 1 minus X. That's because the weighted average puts the average value closer to 63 than it does to 65. Okay. That's just qualitative analysis. Okay, so now all you have to do is solve for X, and that'll give you the fraction of 63. So we have 63X here, and then 65 here, minus 65X equals this. Just doing a little algebra. So if we say 63X, if we combine our X's, then we have 63 minus 65X, and then 63.55 minus 65, because it came from over there and went over here. This is going to be a minus 2x, and this is going to be a minus 1.45. So x then is equal to minus 1.45 divided by minus 2. The minuses cancel out. And so I don't have to get my calculator out. 0.725. 0.725. 5. That's the fraction of isotope copper 63. So if they want the answer in percentage, right, you just multiply by 100. So it's 72.5% copper 63. Okay?
I have a question about 27.
Okay. 27. There it
If
is.
we could do that one.
Yeah, sure. Let's see, you take an aspirin tablet. We know it only has carbon, hydrogen, oxygen in it. Nothing else. That's important. Doesn't have anything else that's hiding in there. And it has a mass of 1 gram. Let's see, you burn it in the air and collect 2.2 grams of carbon dioxide, 0.4 grams of water. Okay, that's a good one. Everybody got this one? Okay. This is actually what the analytical chemist would do in the lab. Burn it in oxygen and collect the gases. So let's see if I can do this without my cheat sheet. What are we given? Carbon, hydrogen, and oxygen. The total mass is 1 gram each, is 1 gram total. So if we want to know the percentage of each one, it's going to be whatever we collect. Actually, it's more complicated than that. So hold that thought a minute. Let's just say the mass, sample mass equals 1 gram. And you collect 2.20 grams of carbon dioxide, okay? And 0.4 grams, 0.4 grams of water. That accounts for the hydrogen. And then whatever's left over is the oxygen, but we don't know that yet. We have to find out how many grams of carbon does that represent. Okay, we got oxygen in there. So what we have to do is say, all right, so what's the ratio of carbon to CO2? Right, so we can do that with 12.01 is carbon, molar mass, and CO2 is 12.01 plus 32 for the oxygen, right? So 12.01 and 32, just divide those, so that's 0.273 fraction. So for every 1 gram of CO2, we have 0.273 grams of carbon. Excuse me. I did my math right. That's about right. Yeah. Got 1/4, so that's like 40, and this is like 10, so that'd be 10. That's about 1/4. I'm just checking myself, estimating. Okay, so what do we have here? Well, we have 0.273 and 2.2 gives us 0.6 grams of carbon. That's how much carbon came out of that sample. So for this one, we need to find out what's the composition of hydrogen in water. So for that one, we need hydrogen. Actually, there's 2 of them, isn't there? 2 hydrogens, H2O. And then we have, this is the total. So that's the fraction of hydrogen in the water. 2 liter, 0.1 times 16 plus. So I need 2. So I get a fraction of that doesn't look right. Let me try that again. Oxygen is 16. Let's see. 2 divided by 18. Yeah, that's right. So the actual number is 2.02 divided by 18.02. See, wrong. 0.121 is the fraction of hydrogen in that. So for every 1 gram of hydrogen, we have 0.121. So 0.121 times 0.4 is 4.84 times 10 to the minus 2 grams of hydrogen in that sample. So how much oxygen is in there? Well, it's 1 minus 0.6 minus 0.00484. Right? Subtract the carbon, subtract the hydrogen, and you get the oxygen. Okay, so I get 0.395 grams of oxygen. Okay, now we know how many grams is in each one. The percentage would then be divided by 1, which is the total, times 100. So we're doing Henry Ford again. So that's 60%, right? Carbon. This is, let's see, times 100. That's 4.84% hydrogen, and this is 39.5% oxygen. Now, see, let's add those up and see. That's not right. Because we got more than 100%, don't we? But what did I do wrong? I probably did something wrong here. 4.84. It's 4.84. 60. You know what I should have done? Actually, I didn't need to do all this, did I? I know these two. This one's by difference. So 60 plus. Oh, y'all just gonna let me go ahead and do that, weren't you? Six. That's what I get for trying it without my cheat sheet. And then oxygen. 4.84. Oxygen is going to be the lion's share of this, isn't it? So 6 and 4.84. And then change that sign. I get 89.2%. See if I made a boo somewhere. 27. 0.3. So this would be, I think I did that right. Yeah, 0.395 grams. You know, I think I'm going the long way around here. All I really need is not percentages, is it? Because as long as you've got grams, you can convert it to moles. So there, I've got grams. Convert to moles. So carbon is going to be like this, this, 12.01. Hydrogen is going to be 1.01, and oxygen is going to be 16. Six. 0.0448. Yeah, that's right. Okay. So we want the mole ratio. Have I confused anybody yet? Okay, let me back up. First trick is to, if this is the carbon dioxide that's collected from that combustion, that accounts for carbon and the added oxygen in the combustion. So we got to convert it to carbon and nothing else. So we got this mass for the carbon dioxide. This converts the carbon dioxide into carbon, because that's the fraction of carbon that is in this molecule. Okay, so that means we actually only have 0.6 grams of carbon out of that original 1 gram. Okay, do the same thing for hydrogen. So it says we get 0.4 grams of water, which means that we got to convert that hydrogen, which, and this is the ratio of hydrogen to water, 0.121 grams for every gram of water. And we got this many grams out of it. So that means we have 0.0484 grams of hydrogen out of that combustion. So all we have to do then, since the total is 1 gram, you just subtract. I did this wrong. That's why the number's wrong. This is 0.0484. There we go. So this is 352. There we go. So that's the mass you have in 1 gram. But formulas are molar ratios. So we've got to find out how many moles does that mass represent, each one. So now we convert using our conversion factor is molar mass. So we've got that many grams, convert it to moles, grams convert to moles, and grams convert to moles. So here we have 4.996 times 10 to the minus 2 moles of carbon. And this is 4.792 times 10 to the minus 2 moles of hydrogen. And this is 2.20 times 10 to the minus 2 moles of oxygen. Okay. The problem with that is it's not whole numbers. So what we need to do is convert that to whole numbers. And the simplest way to convert it is to take the Smallest number, and divide through the whole thing by that. So this is the smallest one. They're all to the -2. So we divide through by 2.20 times 10 to the -2. And see what we get. Well, that was 1, obviously. And this one is 2.178. And this one is 2.27. Okay? So the next thing we have to do is find the simplest whole number ratio out of this whole mess. So what would happen? I know what would happen if we multiply this one times 4. That's almost a quarter. So that would get rid of this one. We can try that. So if we multiply each one by 4, let me see. Okay. I think this one might be off. It's not going to give me what I expect. So that will make this one about 9. This one about 8.7, and that was 4. So I think the hydrogen might be off. I know what's happened. The way I worked it in there, I rounded this one off to 2 since that's such a small number. And that would give you 8 here, 984. But I want to be sure that I didn't make a mistake here. So how about this one? Let's be sure that's correct. That's where I made my mistake. It's 112. Okay, so this is, I'm dyslexic. There we go. So 0.112 times 0.4 is 4/8. There. Divided by 1.01 is 444. And that gives us 2 times 4 is 8. Okay, now it's right.
So we're gonna have like 6 hours to do.
No, I'm not going to give you a problem like that on exam. If you get a problem even similar to that, it's going to be in abbreviated form. So you're given a lot of stuff up front, and then you just complete the calculation. I'd be more likely to give you something where I say the percent composition of this is so much percent carbon, so much percent hydrogen, and the rest is oxygen. And then you take the percent and you use that standard procedure that we went through before. Right, so if it's percent, you assume 100 grams, right? And then your percent becomes grams. And then you convert to moles, do the ratio, and find out. This is the simplest ratio, which would be C There we go. The simplest ratio would then be C9, H 8, and O 4.
Let me see. Am I missing part of the question? The molar mass of aspirin is between 170 and 190. So the molecular formula of aspirin is, okay. So if it's between 170, say 180 as an average.
So if the true molecular weight is, say, something near 180, how do we find out the molar mass? Remember that you need that multiplier of the empirical formula. So you would find out what is the molar mass of that formula, which I call the empirical weight. So the empirical weight then is equal to 9 times 12.01 for carbon plus 8 times 1.01 for hydrogen plus 4 times 16 for oxygen. And that's 9. And then 64 is 180.2 grams per mole. So the empirical weight is close enough to that one, so we can say X equals 1. That's your molecular formula.
Right. Since one is equal to the other one, then you just divide them together to get 1. Okay? That made it easy. So that's the formula, the molecular formula of aspirin. Acetyl salicylic acid.
What is the example?
I think it's Wednesday. Let me check to be sure.
Will it be online?
Only if we're closed.
Okay.
Yeah. If we're open, come on in.
That was a big pain in the butt.
Try.
I hated dealing with that.
I know. I couldn't think of any other way.
Yeah, me neither. I was just like,
Yeah, if that happens again the next time, I'm just gonna print out the hard copy.
Yeah,
So I don't have that problem with the subscript.
that's fine. Yeah. Okay, so any others? In chapter 3, we haven't even got chapter 4 yet. We balanced equations in this chapter too, didn't we? Learn how to balance equations? Or was that last time? Huh?
I think it's good.
4 does that. Okay. Okay, so we'll hold that for a second. Well, there's one that requires balancing. Number 39. I think there are several. I think this is chapter 3. This is where we balance equations. So let me position this again.
So we get this board. There we go.
Okay, so let's try that one. 39. Let's see, ammonia, oxygen, NO2, and water.
Ammonia, oxygen, NO2. There we go. So we want to balance that equation. So we set up our table, our budget. So what do we have to deal with here? Well, we got nitrogen, we got hydrogen, we got oxygen. It's everybody. Now, what do we start with? 1 nitrogen, 3 hydrogens, 2 oxygens. On this side, we've got 1 nitrogen, 2 hydrogens, and 3 oxygens. Okay, first trick, save the elements to last. If you have anything that's just one element, save it to last. And if you have no intuition about where to start, just start at the top. So we've got 1 nitrogen, we leave that one alone. 3 hydrogens, 2 hydrogens over here. So the best way to balance an odd and an even is cross multiply. So if we say 3 here and 2 here, that makes 6 hydrogens here and 6 hydrogens there. But it also changes 2 nitrogens, right? And here it gives you 3 oxygens, plus 2 is 5. Okay? So now, let's go back to nitrogen. So we need 2 nitrogens. That gives us 4 plus 3 is 7 oxygens, right? Did I do that right? 2 times 2 is 4, 3, 7. Okay. Now let's see. 2 nitrogens, 6, 2. 2 nitrogens, 6, yeah, 7. Okay. So, time for our second trick. Use a fractional coefficient as an intermediate step, right? Because you need 7 oxygens over here, but you've got a diatomic, and there's no way you can get 7 out of that with a whole number. Right? So we use 7 halves, right? So that's 7 oxygens. Technically, we're balanced, but we're not the simplest whole number ratio yet. So how do we get rid of that fraction? Multiply the whole thing through by 2. That cancels the fraction. So that makes this 4, makes this 7, makes this 4, makes this 6. So what was the question? What is the coefficient for oxygen? And that would be 7. Okay? I don't know, did I incorporate that thing in here? No, I didn't. Must be in the PowerPoints. The tricks. Yeah, PowerPoints. Plus, it's a separate document in Blackboard if you want to download it. Let's see. How about some stoichiometry? Stop me anytime you think of something that's bugging you. Otherwise, I'll just keep right on going. This is a fairly simple one. 46. So the authors have been kind enough to balance that equation ahead of time. Potassium, what's that compound? Polyatomic, right? So what's ClO3? Chlorate. So it's potassium chlorate. Decomposes when heated to
potassium chloride plus 3 oxygen. Okay? That's the balanced equation. You always have to have the balanced equation. Actually, before that, if you're not given, say, it's a word problem, and it says potassium chloride decomposes into potassium chloride and oxygen. Well, you have to know how to write that. You have to know how to write that. And you better know that oxygen is diatomic. Otherwise, you're dead in the water. Where are the diatomics? There's one. There's another one. Another one, another one, another one, another one. That's all there is. Just those. Hydrogen, and then the inverted L. Okay, back to the problem. We're given 7.11 grams of this. 7.11 grams of potassium chloride. Question is, how many moles of oxygen are formed when that decomposes? Okay, so we want to know, question, moles. How do we get there? Remember the Great Walls? You can't cross those unless you got moles. So you got mass here, you better make moles. So you need the molar mass of potassium chloride. So potassium is 39.10 rounded off. Chlorine is 35.45. And oxygen is actually 3 times 16. Okay? And 16. So I get 122.55 grams per mole. That's the molar mass of this compound. We're going to convert that, right? Top, bottom, cancel, leaves us with moles. That's a 5. Messy, messy, messy. Okay, so I take that one and divide it into this one, and I get 5.802 times 10 to the minus 2 moles of potassium chlorate. Okay? So that's how many moles of potassium chlorate are reacting. So now that you got moles, you can go over there. You got to convert this to moles of oxygen. So what's the magic conversion factor for this one? Coefficients. Your balanced equation tells you the stoichiometric ratio. So you've got 3 oxygens and 2 potassium chlorate. Right? I could write moles in there, but they're canceled anyway. So that cancels this one, and you say 3 times this divided by 2. I get 1.5. Is that right? 5.802. 3 times 2 divided. There we go, that's better. 8.7 times 10 to the minus 2 moles oxygen. That's how many moles of oxygen are produced by the decomposition of potassium chlorate. That many grams of potassium chlorate. Okay? Now, what would you do if the question had been, what mass of oxygen is produced by the decomposition of this mass of potassium chlorate? It's just another conversion, right? If you know that many moles of oxygen, you can convert to
mass of oxygen. You just need the molar mass of O2, which is 32, because you got 2 oxygens there, times that, and that's your mass of oxygen. Okay? That's why I hammered on conversion factors early on. If you don't know conversion factors, you might as well stick your head in the sand. Let's see what else we can come up with. There's stoichiometry. Is there one with limiting reactants? That would be a good one to go next. Because this reaction has only got one reactant. So when it completely decomposes, it doesn't matter how much of anything else there is. It's going to make all of that. But if you have 2 reactants or more, then one of them is usually limiting and the other's in excess. So if you're given like so many grams of I don't know, octane, and you burn it in air, so air is going to be excess, octane's going to run out. So that's an easy one. But if you're given exact amounts, say your octane's in a closed vessel, and it's only got so much oxygen in there with it, then you've got to decide, well, with that much oxygen, is it going to run out, or is the octane going to run out first? Which one? That's the kind I want to go to next. Let's see. We need one in which both reactants are given. Okay, here's a good one. 59. Okay, I should be writing this thing up here. Yeah. Right, so when you look at the screen, if I'm mumbling, then you can see the number. So here's a balanced equation. Again, you don't have to balance this one. Okay. So I'll tell you, this one's methane. That's chlorine. These are gases. How about this one? It's going to be a gas this time too. That name this compound. Extra credit. Didn't I give you all that one? Okay. So you've done this one already. Carbon tetrachloride. And this one is, if it's a gas, you name it like any other binary compound. Hydrogen chloride. But if it's dissolved in water, it would be an acid, and you'd name it hydrochloric acid. In this case, it's hydrogen chloride. Okay, so what else are we given? 1.2 moles of methane combined with 1.11 mole of chlorine gas. And the question is, what mass of carbon tetrachloride will be produced by this reaction? Okay. The authors have been kind. You've already got moles, so you can immediately go that direction. But how do you tell which one's limiting? one that's limiting is the one that produces the least amount of product. Okay, so you got to convert this one to that and this one to that, and see which one makes the least amount. So if we say 1.2 moles of methane, right? So how much carbon tetrachloride does it make? Well, we need the ratio. Right? So we got one of these for every one of those. That's how much carbon tetrachloride would be produced if we used all of this. What if we use all of that? Moles of chlorine. So we got to get rid of the chlorine and leave us with carbon tetrachloride. So what's the ratio here? Well, it's still 4 chlorines and 1 carbon tetrachloride. So you divide 4 into this. See if I can do that in my head. 2, 3, not quite 3, so 2. And then 4 into, it's about 8. There you go. So there you can compare how much would methane produce, how much would chlorine produce, which one's limiting. This one's limiting. This one's in excess. So when you get finished with a reaction, you're going to have some of that and some of that. You're also going to have some of this left over. Right? So this is the one that produces the least amount. So that's the one you calculate for mass. So what's the molar mass of carbon tetrachloride? Well, 12.01. And then chlorine. So 4 times 35, 45. So I get 153.81 grams per mole. Times 0.28 yields 43.07 grams of carbon tetrachloride. 59. Let me see if I got it right. Okay, I miscalculated somewhere. 1.11 enter 4 divided 2.7, 2.78. I bet that's where it is. This is 78. And then times 53. Yeah, 42.68. That may not even be right. Yeah, close enough. Close enough to find out that D's it. That's the best answer. We still could have got the right answer with that one. See how we're doing on time. 1:30. Oh, we only got 15 minutes. We better jump into chapter 4.
Can we do 77 on chapter 4?
Okay.
Or 77 or 78?
All right. Let's see here. 77 or 78. Oh, balancing those equations.
Yeah.
Okay. Well, pick one. We'll do 78.
Yeah. I think there's just so much there that it's like confusing.
Yeah.
Okay. Let's see how quickly we can get this done. All right. KI. Let me see what method I'm going to use for that one. I want to be consistent. I'm going to use the Redox balance method. Okay, maybe that was the confusing part. Yeah. And HNO3.
Good, how are you?
Okay, and 3. You know, we probably could do this. And it would be a real chore to do it by the conventional method. And then water. Okay. So, where are the electrons being transferred? Remember, oxidation is loss, reduction is gain. And we did cover that in this chapter, didn't we? Oxidation reduction? Okay, good. So what's happening to potassium? Potassium is K is plus, and it's plus here. Potassium is not changing. No electron transfer there. Iodine is -1 here, and over here it's 0. So iodine is being oxidized from -1 to a 0. So loss from -1 to 0, 1 electron per iodine. Hydrogen's not changing. It's +1 here, it's +1 there. Right? -2 for oxygen there. Oxygen here is -2. Nitrogen here is, let's see, that's +1. -2 is -6. And +1 from that is -5. So this has to be a +5. Well, that nitrogen is a +5. This nitrogen is going to be a +5. But that nitrogen is going to be a +2. So one of these nitrogens, I see a problem. I mean, I can see where the confusion is. Let's see, 70. Yeah, that could really get under your skin, couldn't it? Okay. All right. Actually, we're going to do it in 2 steps. We're going to balance electrons first. Then we're going to finish with conventional balancing. Okay, so what we've got to do is say if that's loss, this has to be gain. How many electrons? Well, from +5 to +2 is how many electrons? 3. Gain 3 electrons per nitrogen. So now we're going to have 2 iodines here equals 2 electrons, which means this needs to be 2. Okay, and but this is 3 electrons and that's 2, so we're going to have to cross multiply. Right. So if we multiply these times 2 here, 2 nitrogens equals 6 electrons. Okay, now we need 6 electrons from here to here. We've already got 2. So if we multiply this again by 3, we have 6 electrons. So 3 times this one is 6, and 3 times this one is 3. Okay. Now, at that point, you've got balanced electron flow. You just don't have a balanced equation. So what we have to do is we have to take this equation now we can finish it off the conventional way. So we've got potassium, iodine, hydrogen, nitrogen, and oxygen. And the reason that I've got to separate the nitrogens and oxygens, even though we have a nitrate here and here, is that we also have an NO there. So it split the nitrogen and oxygens, and we have no choice but to keep the elements separate now. I know that trick where if you have a polyatomic on both sides, as long as it doesn't split in the process, you can use the polyatomic to balance, but not in this case. We have to split them up. So in this case, we've got 6K, and iodine is 6 iodine, and hydrogen is 2. Nitrogen is 2, right? 2 times 1, and oxygen is 6. Now let's see if I got that right. 18, 22. So that's 12, 14, 16. That's 19. Okay, I made a mistake somewhere. 6K, 6I, 2 hydrogens, 2 nitrogens, 6 oxygens. That should be right. I must have counted wrong. 10. I did. That's 22. And this is 6 plus 6 is 12, 14, 16, and 6 is 22. Okay, that's good. Now this side, how many Ks do we have? 1. How many nitrogens? We got 1 and 2 is 3. Oxygens. We got 3, 5, 6. 6 oxygens. And I need iodines and hydrogens. Let's see, hydrogens are 2. And iodines, 6. Okay. We do have element here, so we can hold that one to the end. Even though it's already balanced, we're going to mess with it in a minute, I'm pretty sure. What if we say potassium? Make potassium 6. So what does that do to the rest? Okay, potassium, nitrogen, 6, 7, 8. 8 nitrogens. Okay. And 18 oxygens, 20 oxygens, 21 oxygens. Okay. Hydrogens, nitrogens. We need 8 nitrogens on this side. Right. So that gives us 8 nitrogens. That gives us 8 hydrogens as well. Oops, wrong one. And it gives us 24 oxygens. Right? So iodine still seems to be okay. Hydrogens and oxygens. Did I count those right? That's 24 oxygens. 1, 3, 18 is 21, yeah, that's right. Okay, so hydrogens. If we want 8 hydrogens on this side, we need 4 of these, right? Okay. And that gives us 4 oxygens plus 2 is 6, plus 18 is 24, right? So how did I end up with only, oh, I miscounted. That's 8. Here we go. Now it's balanced. That's a challenge. And I wouldn't give you one of those except maybe as a bonus. Because if it took me, what, 15 minutes? Right. It would probably take you 30 minutes. So I wouldn't do that to you. Not as a required part of the test. In fact, I wouldn't even do one that complex for a bonus. Okay, so are we out of time? Okay, what about, let's see, I want to be sure everybody, let's go back to chapter 3 for just a second. Everybody understands how to interpret page 16. Those little pictures. Can you derive the empirical formula from those pictures? Well, the first one, you count up the carbons. You have 6 carbons and 6 hydrogens, right? So C6H6, what's the empirical formula of that? Divide through by 6, right? How about the second one? 2 carbons, 4 hydrogens. So that's C2H4 simplified as CH2. Just divide through by 2. C is a little more complicated. You have to count up all the carbons. I see 1, 2, 3, 4, 5, 6. So it's C6. And then hydrogens are 3, 4, 5, 6, 7, 8, 9, 10, 12. I know where this one's going. 1, 2, 3, 4, 5, 6 oxygens. That's glucose. But simplified, it's CH2O.
So you just divide it until it's like the smallest number?
Right. Divide everything. You have to keep the same ratio, right? 6, 12, 6 is the same as 1, 2, 1. You want the smallest whole number ratio to give you the empirical formula. How about the last one? Carbons, we got 1, 2, 3, 4, 5, 6 carbons. Hydrogens are 2, 4, 6, 8, 10. And oxygens are 2. So the smallest divisor, or the largest divisor you can put through that one is 2, right? So C3H5O, well, we don't write the 1. Okay? Okay, let's see. Is this one, we do, excuse me, precipitation reactions, different types of reactions. Maybe not. Oxidation states, you know how to do those, right? You know what the standards oxidation states for the rest of them are. If it's a pure element, it's always 0. If it's a halogen, at this point in our studies, halogens are -1s, -2 oxidation state, and +1, +2, +3. The rest of them you can calculate. And when you have a molecule, if it has no charge, then all your oxidation states times how many there are, how many elements there are, have to add up to 0. you have a polyatomic ion, like that, then your oxidation states have to add up to the charge. Right? So -2 here would be -6 total. And pull one out for that minus, that means you have to balance a -5. So nitrogen is +5. Okay? Practice, practice. Let's see. How big a test is it? Oh, it's short. 39 points and 27 points of bonus. And it looks like each one is worth a point. Yeah. So it'd be 39 questions, required 27 extra credit.
What was it last week?
What was what last time?
How many questions was the test last week?
Oh, the first one,
Felt really long.
was it long?
It felt long.
Ooh, 86. Yeah, the first one was kind of rough. This one's a little more manageable.
I had to take
But-
it 6 times too.
But some of the things require some calculations here. That's why I shortened down and made fewer questions, because it takes a little longer to work each one. The first one, a lot of them are just memory. Okay? So I'm going to try to get this on the Blackboard sometime this evening. Certainly by tomorrow morning. I don't want to take up too much time because you guys need to see it soon. Oh, and we have a lab Wednesday too, don't we? Waters of constitution and hydration? Yeah, okay.
And,
Have I checked your notebooks yet?
check those.
I check those on Wednesday, don't I? Okay. Let's see here. Stop the recording.
Notes on the